Professor Landremont, who is my good friend from, I was going to say MIT, my good friend from the Technion. He will introduce Professor Zexiang, who is graciously participating in this conference. And it's another, Madlik, how do you say that? Another enlightening talk that we are going to have today. Please.
So I'm really honored to present our next speaker. Professor Zexiang is a full professor at Hong Kong University of Science and Technology. Professor Zexiang, in addition of being first-rate scientist in robotics, he is also an amazing industrial entrepreneur. And I should mention two companies that he owns, manages, and they're extremely successful. The first one, it's a motion control company called Google Tech, and which has contacts with Galil Motion Control here in Israel. The second company, I'm sure you all heard about, it's too famous not to know about, it's called TJI. It's a drone company that makes a very famous series of drones that fly and have those automatic cameras. In fact, this month, the prestigious Wired magazine has a special article on this company. I just actually finished reading it very carefully. It turns out that they are controlling something like 70% of the world market. So it's really amazing. Last, Professor Zexiang is the author of the famous Lee, Mary, and Sastry book on robot control and robot grasping, which is still considered the dominant textbook in robotics. So please welcome Professor Zexiang.
Thanks, Elon, for the introduction. It's a great pleasure to be here. I know that, from all the talks today, autonomous driving is regarded as the, problem or biggest challenge and also biggest opportunities for robotics. And today, I'd like to convince you that there's another problem, which is manipulation and the autonomous assembling of small parts products, such as the iPhone that you have, is a problem of at least equal magnitude in terms of impact. Okay, so today I'd like to share with you the work of many who have contributed to the development of the understanding of the manipulation problem. Okay, but before that, I tell you the story how I got involved into this problem. Okay, it was sometime probably 1982 when we were all undergraduate students. Okay, at CMU. Okay, Robotics Institute was just established. And I took a course in robotics and was frustrated, because of my poor hands-on skill. I have no sense what the homogeneous transformations mean. Okay. So then I went to Berkeley and I volunteered myself to organize the graduate robotics seminar. I invited Mark Kakowski and also Yushi Nakamura to give 2 seminars on multi-fingered manipulation, okay? Because I have a pair of hands, so I was very impressed by the complexity of the motion. But at that time, the only mathematical tool available to understand such complex motion was screw theory. Okay, I was pretty much screwed up by it. So then one day, my advisor, Professor Shankar Sastry, brought me a paper by Roger Brackett on the product of exponential formula. And there, the relation between infinitesimal motion and the finite motion, at least for the case of Euclidean group, was beautifully displayed. I immediately fall in love with it and spent the next 30 years, try to understand it and also make use of that to understand the problem. Okay, and also this talk is a tribute to many of the people who made the contribution. Okay, so here is a outline. I know, it's very late in the afternoon, and I will try to be just as brief as possible. And I will briefly introduce the geometric tools, okay, and connect that with the problems in manipulation. Okay, those are very geometric in nature, and they are interconnection. And also, I was very fortunate to be involved in the startup of a few companies with my students, where the geometric tools or theory played a fundamental role. Okay, so we are trying to bring that experience and also resource to more young robotic entrepreneur. Okay, and I think finally the time is mature to address this grand challenge problem. How do you automate assembling of small parts products? So we all know that the geometry can be roughly classified or separated into the Euclidean geometry and the non-Euclidean or the modern geometry. And we know the work of Euclid from elements and Descartes by using coordinate system. So you can describe points in space by 3 triplets or n-tuple of numbers, right? And Newton, Leibniz developed calculus on top of that. And also Gossip Munch introduced calculus to engineering. So today we know that either by simplification or approximation, all engineering problems or lots of engineering problems can be formulated as a optimization problem in Euclidean space. And the non-Euclidean geometry or differentiable manifold, Gauss introduced that for dimension 1 and 2. His postdoc Riemann generalized that to dimension 3 and higher. Selflessly, Klein introduced a special class of differentiable manifold. And the notations we use are due to Hermann Weyl, and the SS chain is, produced a great impact to the Berkeley math and the engineering program. Jerry Marsden built the bridge between the math program and also the engineering program. So the application of non-Euclidean or non-Euclidean geometry to kinematics, the classical history of geometric robotics probably start with Franz Rowley. Okay, he discovered that region motions generated by the 6 lower pairs all form subgroups of the Euclidean group, and they, of course, Bohr, developed the kinematics or screw theory, and of course later the chairman of IF told me this is a big community on that, and also the names which are pretty much familiar, okay, to the community, and I think V is probably the cutting off point. He is between the classical and the modern geometric robotics. So the modern geometric robotics, I would really credit to the work of Roger Brackett for the product of exponential formula, which I will explain it later, and also several of his outstanding PhD, David Montana, Lon Carrick, Frank Park, made profound contributions to this area. And also the Berkeley group, Shankar, his PhD students, Payton, Richard Murray, and actually EMI extended the same tool to 3D computer vision, okay, in that textbook. And of course, the MIT group, And Ramon and with Joe Burdick applied the geometric tools to multi-body contact, and also the names here, and also Martin Booth on grasping force optimization, and Tony Beach, non-holonomic hands. And Vijay Kumar extended the tool to quad rotor trajectory generation and control. So the names can go on, okay, and I may apologize if I miss lots of names here. So here I like to just give you a short list of problems which I believe are geometric in nature. If you understand the geometry, you understand pretty much those problems. So the first problem is dynamic, how do you describe rigid body motion, including the kinematics, trajectory generation, dynamics, stability control, etc., etc. Okay. The second class of problem is for open chain manipulators, and the forward, inverse dynamics, control, all those issues. And the third class of problem is multi-finger hands. And how do you model the kinematics of contact? And how do you model grasping force optimization problem, and all those. And the fourth class of problem, parallel mechanism. And the examples are listed here for the analysis, synthesis. And the fifth class of problem, there are a few very special mechanisms, including the shoulder joints for our shoulder, the eyeball movements. What are the precise tools allow you to describe the motion type of those mechanisms, and also be able to synthesize versions related or from that. And the machine tool design, the CV joints, the parallel spindle head, and also for their precise modeling, analysis, and the synthesis. Okay. And the non-holonomic motion planning system, including how do you manipulating an egg object within your hand, and you understand how a falling cat lands on the feet, okay, and also parallel parking a car, okay. All those problems are similar in nature, and they are called the non-holonomic systems. So for their modeling, planning, control, etc. Okay. And the eighth class of problem is tolerance notions, okay. Because to control the quality of products, you need to have various notions of tolerancing. Okay. What are the right mathematical tools to formulate those notions precisely, and use that for their verification? And also workpiece localization, okay, of symmetric, non-symmetric, and also partially machined workpiece is critical, okay. And how do you model those problems? And today we see that dual arm systems are increasingly being utilized. Those we call the left and the right hands. How do we have a tool to model those systems, and also for their synthesis and the calibration? And today, all the assemblies are done in the fashion of work cell. Multiple robots are involved in a work cell. And the 3D sensing is very popular. So we can have a precise model of the workspace. That will allow motion planning techniques to be utilized, and also for calibration of such a work cell. So these problems can go on, and there is a long list. And I like to give a brief flavor of the, okay, sorry that the latex doesn't work on here. And so if we have a function defined on Euclidean space, and we wish to minimize the function, right? What do we do? Well, we try to find for the critical points, then look at the hashing, right? To decide if that is a minimal or maximal. And to find the critical points, we have to compute directional derivative, okay? And to compute the directional derivative, we have to use geometric property of the underlying space. So unless you know the geometric property of the underlying space, it is difficult to do it. So in the case of, we wish to extend, calculus on Rn to calculus on manifold, okay? Of course, you will ask, what is a manifold? I just give you a simple example. If you have a unit sphere, how do you describe points on a unit sphere? You use latitude and the longitude coordinates to do that, right? But if you do so, you will run into singularities, which are the North Pole, South Pole, meridian line connecting the North and the South Pole. So to capture every point on the surface, you have to introduce another coordinate system. And hopefully its singularity will not overlap with the red one. And for points, in between, you have red coordinates and also yellow coordinates. And you impose the change of coordinates, be smooth, okay? So those kind of coordinates are called compatible, okay? So if you pile them up, you will get a differentiable structure. So the unit sphere with a differentiable structure is called a manifold, okay? And in robotics, manifold abounds, okay? Rn, okay, is one example. The configuration space of a 2 degree of freedom revolute joints is a 2-dimensional torus, product of 2 unit circle. And a 6 degree of freedom industrial robot is a 6-dimensional torus. And there's a special class of manifold, okay, in the case of the sets of rotations. Okay, we realize that if we multiply 2 rotation matrices, we get a rotation matrix, right? So the group operation and the manifold structure are compatible. So that is called a Lie group, okay? Surface Lie introduced that. And also the special Euclidean group that we use to represent the Euclidean motion of a rigid body is also a Lie group. And if a unique advantage of a Lie group is that it has a canonical coordinate system given by the exponential map. Okay, so that any Lie group, you take the tangent space at the identity, and in the case of the rotation group, all the 3x3 skew symmetric matrices. And in the case of the special Euclidean group, the set of twist elements. Okay. And the exponential map for rotation is simply rotation about a fixed axis. And for special Euclidean group are screw motion, okay, along an axis. Okay, so if you have a linear space, then you have a subspace. You have a Lie group, then you have a subgroup. And we realize motion generated by revolute joints forms a subgroup. And also motion generated by the 6 lower pairs form subgroups. Okay. And using this exponential map, you can formulate the forward kinematics as a product of 6 exponential. That is a bracket POE formula. And using this elegant formulation, you have a beautiful description of the Jacobian, the inverse kinematics, and also study optimal workspace design. Okay. And also, you can formulate the falling cat problem as a nonlinear control problem over the product of 2 rotation groups. And you will show this is a control system, controllable system. And there are certain subsets of a Lie group that is not closed under multiplication, okay, but still smooth. Those are called submanifolds, okay. And this is a special class of submanifolds that is given by the exponential of a subspace in the Lie algebra, which is closed under triple bracket, not double bracket, okay. You can use that, and this is called the exponential submanifold. This is used to describe the motion of your eyeball, the motion of the CV joints, the motion of your shoulder joints, okay. No other better mathematical models for that. 5 minutes, I will. So Riemannian manifold, if you have a metric, and then you can define geodesic and all this. And in robotics or rigid body motion, using kinetic energy as the metric, the Newton-Euler equation becomes the geodesic equation. And then you have the dynamics of the open chain manipulator algorithm that is ON. And also can be factorized for later control algorithm design. And also for grasping of multi-finger hands, you can formulate that as a convex optimization problem in a Riemannian manifold. Okay. So, and also homogeneous space, I will probably just take 1 second. If you want to describe motion of a symmetric object, such as a cylinder, it has a symmetry. Okay. So the configuration space of this is simply the quotient by its symmetry. And using that formulation, you will see that the workpiece localization becomes a least square problem in the homogeneous space if you have a symmetry. Otherwise, it is takes place in the Euclidean space. And also the notions of tolerancing. Okay, this is a very if you use vector calculus, it is terrible. You have to have one formulation for each different cases. But if you realize those are all about displacement of symmetric features, then it becomes a minimax problem in homogeneous spaces. And the algorithm that you have is very precise. Okay. So in the next 4 minutes, okay, I will just go through briefly, what those algorithms allow you to do. Well, your program will be very compact, very efficient, and you will do a lot of things online instead of offline. So the first company called Google Tech, we use some of those geometric algorithms for the motion control of various machinery. Those are some of the products that we have. Okay, this now today is a major motion control company in China. We have around 50% of the market share. And they also that, remember, when I was an undergraduate student, I didn't have the opportunity to do hands-on. So when I become a professor, I try to provide them with both hands-on skill and the geometric, tools for them. So I had a course to teach students on robot competition, and a group of students come off from this course become entrepreneurs. So they have geometric reasoning, and also they have experimental tools available to them. Okay, those are some of the students who went on to have their own companies. Okay, Wang Mingyu is one company, DJI, Wantao, and there are many other examples. So actually, Frank Wang, he took the course twice, and for his final year project, he built a controller for a helicopter. And later on, he thought he might sell a few controllers to hobbyists in the community, so he set up a company called DJI. And those are some of the earlier products, and the flagship product is the Phantom, which is out of the box, ready to fly drones. Okay, and also those products won lots of awards, including the best product from the Times Magazine, and also best design from Times Magazine. And also this, is a history in the drone community as we, close the chapter of DIY, okay, into a integrated product. And also the company today grew to more than 5,000 people last year, with more than 1 billion revenue, okay. And also the QKM, and you understand where does the name come from, derives from the quotient. Okay, we have the geometric tool to design robots, and this company is targeting at, precise assembling automation solution. And okay, so I will now go through this problem. Okay, and this is another example, and those are some of the more examples. And also, I think one thing, over the last 20 years or so, the students went through lots of experience and, success, failure. And we believe those experiences are useful, okay, to, entrepreneurs in the robotics community. And, this is the place where we are, Hong Kong, Shenzhen, and Dongguan. This place has a nickname called the Hollywood of Makers because of the impressive supply chain all around here. Okay, you have all kinds of design company, logistic components, and the manufacturing company. You can reduce your, deployment or the development cycle from a month or from years to 1/10 of the time. So we felt this environment might be very useful for students from around the globe, especially maybe students from Israel. Okay, so we decided to establish a robotic incubation facility with all the experience and all the lessons we learned. We tried to provide them with the critical components they need, and also the supply chain, and also even angel fund to them, so that they can go from stage to stage, and they can realize their dreams, just like Frank Wang of DJI did. Okay. So I think I will not go through this, and I think 1 minute for the last grand challenge problem. Okay. So I think the C3 stands for, communication, computer, consumer products, okay? And 70% of all those products are manufactured in China, okay? And this industry employs around probably 50 million or 25 to 50 million workers to assemble the various gadgets, okay? And if you, those are the various processes, okay, from components to module to the final product, okay. And they are mostly done by workers. And I will not show you the video. I think you can Google the Foxconn video, which employ 1.6 million workers to assemble these products, okay. And this is not very much different from some 80 years ago, okay, the same scenario, okay, exactly takes place in the vast amount of factory. And we hope that we could, today fully manual, okay, assembly line, and they become step by step, automated. And this will not take place overnight. It will take place gradually. And the next stage, perhaps some of the critical modules will be accomplished by robots or by work cells. And then eventually, we hope to be able to automate the whole process. Okay. So there are lots of grand challenging problems, including those problems that I highlighted, which I will not go through those problems, because this industry is very different from the automobile industry. The life cycle of this, instead of 10 years, is only 1 year, okay? And the cost is very different. So the challenge is completely different. And I believe that, the work of the robotics community over the last 10 or 20 years, probably make us ready for this, address this grand challenge. Okay, so I think I will conclude the talk. Okay, with a few highlights. The geometric robotics should be provides a rigorous, precise, and also unified tool for treating diverse, complex behavior of various robotic systems. And after 30 years of development, the theory are mature, the algorithms are ready. And now, just like the autonomous driving, C3, manufacturing automation become another grand challenge problem. And the key, rapid iteration, fast scaling up. Okay, those are the key issues we have to capture. Okay, thank you.